Hmm. All right. Well, we're gonna get started with the homework assignment. So how did that go? Okay. Huh? No. Was it? I'm on the wrong one. Today is Monday, Wednesday. Okay. Well, maybe I'm on the wrong one. Recursive? This one? Okay, you're correct. So this one is due on Wednesday. Okay, got it. Fib, we all fibbed. Let's go fibbing. Mm-hmm. Mm-hmm. Okay. All right. You are brave, man. You are brave. Yeah, I think that would be good. Wednesday. Okay. All right. All right. So we're gonna take a look at the C code first, okay, just to make sure what line 5 is. I mean, your entire task was to implement one line in the C code. Okay. So, hmm? Okay. That one single line, which is line 5, is not easy. Okay. I wouldn't say it's easy. It's not super duper hard, but it's not easy. And I will start with the approach. In other words, how do you write the code? Instead of just giving you a solution, it is more important to show you the steps. Okay, how do I start? What is the next step? What is the next step after that? And so on. Okay, because those skills are transferable to the next programming class. Okay, so we're gonna start with that. All right, so I'll just kind of copy this line to the other program and fib.ttpasm, kind of stash it here. Okay, comment it out. All right, so first thing first, we have to understand by the time we get to function f, what is on the stack. Okay, that's always important. So one thing you can do is simply to put a halt instruction here and stop right there. Okay, so this way you can kind of visualize what is on the stack. It is also important to understand the program, by the time we call, because that's how we set up the stack. So every time we see a decrement D, we're putting something on the stack, or we're reserving some space on the stack. So that means, oh, okay, let's count all the decrement D. There's one over here. And then once we get to main, there we start with this one here, which pushes the 3 on the stack. And then we see this one here, which pushes the return address on the stack. So by the time we get to F, there are 3 bytes on the stack that are used already. So it's always good. Personally, I would do this for every single program, just because, it makes it possible to um, just making sure. Yep. So we're going to go to not secrets. You guys cannot see my secrets. So we're going to put it here. Oh, okay. I just clicked the wrong button. So go back to shared. It's not comforting that shared is only one item off from secrets. I have to spell secret in a different way. Maybe put in an underscore first so I don't accidentally show the secret. Just ideas for the exams and stuff like that. Which I constantly get, from talking to people when people ask me questions like, huh, I can turn it into a question. Yep, exactly. All right, so we start with 255, typical thing. Okay, this is this one minus one. just give it a bunch of cells. Okay, I think this time we need 3, 4, 5, 6, 7, 8, 9, possibly that much. Okay, and then we convert. Hmm? Yep, decimal to hexadecimal. There we go. All right. So typically I use this column for the actual value in that location. And then over here we describe what it is for. So this is just the return address from main to the entry code. Okay, fairly standard. And according to the program, okay, so we'll go ahead and know exactly what that number is supposed to be. I used LDID 0, okay, so that means this should be a 09. All right, so if you're still thinking about why is it a 09, we have to do some counting here. This is byte 0, 1, 2, 3, 4, 5, 6, 7, 8. That's byte 9. Okay, so that's how I counted. But the actual expression to specify the 9 is dot 6 plus because the offset to the LDI instruction itself is already a 3. So when you add 6 to 3, you get 9. All right. So now we want to continue with the analysis of what is on the stack. We already know that we push a 0, 3 first. The role of the the reason why we have a 0, 3 push next is this is argument, right? This is argument n of the first invocation of calling function f or fib. Cannot remember whether it's function f or n. Yep, it's just f over here. So is that okay? Yep. Oh, okay, we need x first. Okay, thank you. So in that case, it is unknown. It is my local variable x of main. Then we push. So that is the reservation of that byte is done here. So it's not a decrement, it is a subtraction from the stack pointer. That's how we allocated the local variable x from the stack. Thank you for the correction. And now we have the 0, 3, which is the parameter n of function f, and then we have the return from the first invocation of f back to main. Okay, so this is the return address from the first invocation of f to main. And we can, I mean, I can calculate it, but it's going to be quite painful. Do you guys want to see how to calculate it? No? Yes. Okay, I see people nodding. Okay, so we'll go ahead and pretend that we want to do it. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so it's 25 in decimal, which means it is 1 9 in hexadecimal because 25 is 16 plus 9. So I'm going to say 1 9 in hexadecimal. Okay, so we'll say this is potentially 1 9 in hexadecimal. And by the time we stop in the program with the halt instruction, we're right at the entry point of the callee, which is the first invocation of f. So the stack pointer should be pointing here. So I'm looking at the code that was provided to me as an exercise, okay, in order to understand what is on the stack, where's the stack pointer, what is my starting point from the perspective of the function, okay? So I just turned something that was not a homework assignment, something that was not study material, into study material. Okay, so that skill is really important, okay, in any type of STEM class, is you don't want to wait for your professor to give you homework assignment to practice on. You look for those, okay? Every single time you look at something, you ask, can I explain this? Do I know why this is the way that it is? So do not wait for the professor to ask, I want you to explain, okay? You ask that question in your head and you go like, okay, can I explain this? Do have I learned enough to figure this out by myself? Okay, so if you do this kind of, I wouldn't say constant, but on a regular basis, okay, you'll be way ahead of your peers. Okay, because most people wait, and if you're the ones who do not wait, then you're way ahead of your peers. All right. So we're going to run the code and see if that is really the case. Okay, so we save the code. We switch to a different prompt. We go to Documents, CISP 310, Reaper Spider. Okay, it is really, I just personally like to do it this way because it's handy and I can make tiny little changes to the program and just kind of check in first. So we'll go ahead and submit fib.ttpasm. Okay, there we go. Okay, object code is good. Starting simulator. Okay, so now we go back to the assembler, which apparently is not here anymore. That's okay. We can just kind of go to processor and go to the assembler, go to the analysis tab. Okay, so we see, the first um, overriding is to location FF and is a 09. Okay, that matches our expectation. And then we skip 1 byte. Okay, so FE is only reserved, but we didn't write anything to that location because we can see that we decrement from the stack pointer by 1. So the stack pointer became FE, but we did not store anything at that location because all we did was to reserve a byte on the stack for the local variable. And then we push the 3, and then we push the 1 8. I'm off by 1 byte. I said 1 9, it is 1 8. So I somehow miscounted by 1. I can always go back and watch my own video to find out which byte I miscounted. I counted 1 byte too many, not 1 byte too few. I skipped 12. Oh, okay. I see. I see. I see. Okay. That, well, I mean, at least we could explain that. All right. So very good. So everything is accounted for. So when everything is accounted for, I can now say, okay, what can I do in F right now? Well, I can define the offsets. So I can say LVS is a 0. We don't have any local variables in this case. And then F underscore N, which is the offset to parameter N from the base of the frame in function F, is going to be F underscore LVS 1 plus. This one has to do with the return address on the stack, and it is right on top of the last local variable. Now, we don't have any local variables, but the return address is still there, so you still have to add that one to the 0. So this is where we can find n. Now, it's up to you to decide whether you still want to subtract 0 from the stack pointer for quote unquote allocating for the local variable that does not exist, and then to reclaim that space later on. Okay, so that's just for consistency purposes. So that part is up to you. And then we do a LBD D, increment D, and then we do a JMPB. We jump back to the caller. All right. So, very first thing that I would do, okay, especially if you are not confident about, okay, do I really understand how this all works? The first thing I would do is simply to return, okay, test code, just return n. That's all I want to do. Because this allows me to test everything about this function, the entry, the exit, can we access n, okay? It tests everything that I need to do before I can do the rest. Because if I cannot get to parameter n, I don't have to bother with the rest of the function. Okay, so I need to make sure that I can, in fact, store, get to n. So that code is going to be LDI AFN, which is the offset from the base of the frame to parameter n. And as it turns out, at this point of time, the stack pointer is pointing to the base of the frame. So if you add the stack pointer value to the offset, then you get the address of n in this case, but it is not the address that I want to return. It is the value that I want to return just for testing purposes. So I need an LD instruction to get to the actual value of the parameter. And I'm just going to leave it like that. Okay. So as it is not the function that you really want to implement, but it gives me a chance to verify that everything is working at least up to this point. So I should see local variable x of main getting updated to a value of 3, as the code is at this point. Are we good so far? Okay, so getting back to the map of what the stack should look like. So if I go back to this map over here, that means in this case we should see this to change to 0, 3 as well. Okay, so we're gonna run the code, make sure this happens, because if it does not, then it doesn't make sense for me to move forward, in any way. Yep. Hmm? Oh, you mean this one? Yeah, it's okay. We'll just say, we don't know what it is. We'll let the assembler calculate it. Yep. All right. And then the stack pointer, because I let the program proceed all the way, so that means the stack pointer should go back to 0, 0, which is not going to be any location that we see here on the screen. All right. So we go back and then we make sure we save the code because I'm infamous for forgetting to save the code first. So now we test run it again. Test run it again. All right. So now we get back and then we look at the assembler, go to the analysis tab, and we just kind of go like, okay, let's go all the way to the end. This is the overwrite at location FE. We got a 3. The stack point is balanced. We get to the halt instruction that we're supposed to go back to. So everything seems good, okay, as far as I can tell. So that means I can now proceed. Now, this is where I want to introduce a concept that might be new to some, but might be, some of you may be familiar with that concept already. So I'm going to create a new folder. We'll just call it fib. And then we're going to move fib.ttpasm to fib as a subfolder. Go to fib. So what I'm going to do is to do a get init. Okay. So I'm trying to introduce you guys to the command line called get git, which is associated, affiliated, or related to GitHub. So GitHub is a Microsoft um, web presence to let people host their remote repositories for free. Okay, if you do not know what GitHub is, you should get to know it, at least understand what it is, how to set it up. It's all free. Okay, but I want to show you what get as a command line can do. Okay, this is the initialization, gave you a bunch of messages. And the first thing I need to do is to specify what files do I want to track. Okay, so I want to track only one file in this case, which is fib.ttpasm. Okay, now that doesn't do a single thing other than telling the repository that, oh, I wish you could help me track this particular file. But there's not a single snapshot yet. Okay, so to create a snapshot, you specify, you say get commit fib.ttpasm. So this is like taking a snapshot, pressing the shutter release on the camera, and then it will ask you, okay, what is special about this snapshot? Okay, we'll specify. Okay, verify that I can access parameter n in F. Okay, which is good because I verified it. So I know at this point in time I could at least do that much. So that means later on, if I continue to work on my code after a year or so, and I totally mess up my program, it's not even working to this point. Guess what? I can compare the code. Okay, so I can do something like this. Okay, in other words, this is what I can do. I can go back to the same program and I just go to a random line. I really close my eyes here. I have no idea which line I'm in. And I'm going to say to delete. There are 2 lines deleted here. Save the code. Okay. So this is my simulation of, being drunk and still continue to work on my program. Not a good idea. Okay. And now we go back to run the code again. Hopefully, oh, I did something. Oh crap. Okay, what did I do? I deleted the program itself? Oh no, because I moved the program. That's why. That's okay. That's okay. Yeah, I remember I did not do any RM, so I know I did not remove a file. All right. So now we go back to the trace. Hopefully it is wrong this time. No, it did not affect it. No. Oh, no, 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 no. Don't tell me. Okay, to repeat, a certain radio station's program. Wait, wait, don't tell me. Is that it from NPR? I believe that is the name. Okay, so this is a really cool feature. You can say get div, give it the file name. It tells me exactly which two lines I deleted. There are two lines of comments that I deleted. Okay, but you can see how it is useful, right? Because if I'm drunk, I go to one particular line, I make some random changes and come back and go like, why is the program not working anymore? Diff, okay, diff. But it is only useful if you take a snapshot when the program is verified working, at least to a certain point. Is that okay? All right. So there are ways to retrieve this version and just say, okay, I want to revert back to this particular version. Okay. But I don't need to do that now. Okay. But it's good just to be able to compare. All right. So now we can continue. Okay. We'll go ahead and continue with this code. So yeah, I remember there are some extra lines over here. I just removed some of those comments. All right, so now that I can do it here, I'm going to say, okay, we are not doing this test code anymore. And instead, I want to know whether I can make a decision whether n is less than 2 or not. Okay, so I'm going to take this line and say, okay, this is what I'm going to do now. Okay, this is my new test code. My new test code is just saying, okay, if n is less than 2, we'll pick one particular value to return, let's say 42. And if it is not, we're going to pick another number to return. Let's just say, I don't know, 15. Okay. So this is the new code, which has the same structure that I need to implement, but it doesn't have the actual content of the code that I want. But it does make it easy to debug, right? Because I can now test, did I get a 42? Did I get a 15? Okay, based on the value of n. Are you guys still following me of what I'm trying to do? Okay. So now we implement this test code, which is really the conditional statement structure. So I know by this time A already has n in it. So that means in your case, commenting to know what is in each register is really important. If you have not been doing that, I would highly recommend doing it. Okay, comment on each line what is in each register. Okay, because that's what you need to track in order to implement the programs, and also to to be successful in the final exam. Okay, so you're practicing what you need to do anyway, so might as well do it. All right, so I need to compare n to 2. Well, I can compare to 0 really easy, okay, because that's just an and AA. But comparing to 2, I really need to compare. So I need to put the constant of 2 into another register. Let's say register B. It can be register C2. And now we have to compare. So whenever you can compare in two ways. You can compare, in this case, AB, or you can compare it as BA. So there's no correct method to do it. It all depends on what you do after the compare. Okay, so if you want to maintain the structure that I typically do, which is we want a conditional branch to the else branch, then you want to reverse the compare because you're basically saying, tell me when I should go to the else branch. I go to the else branch when n is greater than or equal to 2. So that means I need to see if 2 is less than n. So that means we need to do a CMP BA. And then we have two conditional branches here. If it is less than, because everything is unsigned, so it's JCI, I want to go to else 0. If it is the same, I also want to go to else 0. Okay, so it is important to remember JCI is only saying less than, but in this case, we also want to cover the case, what if it is 2? If it is 2, I still want to go to the else branch. Yes. Well, okay, so let me finish the structure first and I'll address your question, okay? So I still need to finish up the rest of the construct, which means at this point we have the then branch, but at the end of the then branch we have to get around the else branch to get to the end if or the end of the conditional statement. Then I can specify the actual beginning of the else branch, and then we can specify the end of the entire conditional branch. This would be the else section over here. Now, let me go back to address your question. So JLI works for signed integers. JCI works for unsigned integers. So for the range of values that I can throw at this program, both will work because I cannot really put in a large number because otherwise it will take too long to finish. But conceptually, JLI is incorrect, because JLI is a signed comparison, or it's checking the result as if the two operands are signed, as opposed to JCI, which treats the two operands as unsigned. The JZI is still needed because you still need to catch the case. What if n is 2? Well, if n is 2, according to this, we still want to return to 15. Okay. All right, so now I can simplify the code here and I just go like, okay, according to this test code here, I want to return to 42. So LDI A42 goes here. And then for the else case, I just want to return a 15 over here. So LDI A15 goes here. So now the program should do it should, because I'm still having n being 3. So that means it should return a 15 instead of the 42 as it is. So I save the code, test run it, and then I want to see if we ended up storing 15, which is 0f, to location FE. Hmm? If it works, I commit. Yep. But if it does not, then I go like, okay, I should fix this first. All right, so we will check it out. Okay, we are storing 15, so that's all good. Now, but this is not a good test program because it doesn't test the boundary condition. Because what are the boundary conditions? The boundary conditions in this case is what if n is just barely less than 2? So 1 is a good test case. And then the second test case is what if n is barely not less than 2? So that would be 2. So 1, n being 1, and n being 2 are the better test cases because they test the boundaries of the range of values. Okay? So that means, I don't want to conclude that this code is working yet because I need to retest it. What if it is 1? Okay. And the way, oops, okay, that's not what I intended. So the way I do this is I comment out the original code first, and I comment here, this is test code, so that I remember, okay, later on I need to change this back. So I change it to a 1, test code should have, what was it again? 42, okay, 42 returned, and 42 is, what is 42 in hexadecimal? It is 2 times 16 plus 10, so that would be in hexadecimal 2a. Okay, do you guys see how I do the conversion? Okay, nope, you divide it by 16. You divide it by 16, the quotient becomes the left digit of the hexadecimal representation. The remainder becomes the right digit of the hexadecimal digit. So in this case, 42 divided by 16 has 2 as a quotient and then 10 as a remainder, but 10 in hexadecimal is the digit A. Is that okay? All right. Yep. Yep, because in computer science or in IT especially, there are a lot of stuff in base 16. Every time you look at a MAC address, it is in base 16. When you deal with networking, IPv6, the masks are all specified in base 16, so are the IP addresses. So that's why base 16 is actually quite useful, not so much in computer science, but in the IT field. All right, so test code. Okay, let's run it. Okay, did I run it? Yeah, let's run it again. But this time it should store a 2A in location FE, and then everything else should be the same in terms of the stack and stuff like that. So, yep, we got it. So now I'm going to test the other one boundary case, which is 2. Okay, so we're going to go back to the code. And you can see that I'm obsessive with testing the code because this ends up saving me time. If I don't test the code like this, later on I would discover things later on, and it's just going to be unpleasant when I discover those problems later on. So I test it again. Okay, make sure I save, and then we rerun the code. This time it should be 0F, at the same location FE. Yep. All right, so we are good. Okay, so now would be a good time to commit. So we go back to, yes, yes, yep. But now I can kind of return it back to here because I'm done testing the boundary conditions. So I go back to here, and this test code is all done. Oh, right, I need to kind of check it in or commit. So get commit fib fib.ttpasm, and I just explained, okay, verified that the ternary expression structure is done. Okay, so now I can go into one of the branches. I'm going to target the easiest branch first. So the easiest branch is the then branch, right? Look at this. That's easy because to do that, I just have to do this. Because it is exactly because register A already has the value of n. Okay, that's pretty easy. So we're gonna test it again, right? Actually, I don't need to test it again. Okay, I'm pretty sure that's gonna work. So I can now move on to the recursive side. So the recursive side is nasty because it has two calls. So you need to make sure that one call is working first, okay? Because if you cannot get the left-hand side call to work first, forget about it, okay? It's not going to work. So we are going to test code again, okay? We're going to implement some test code in the else case. So instead of using the original, we just go like, I'm just going to do some random shit here. Yes, I just said the word. Yep. I'm just going to do some random shit here and go like, whatever, okay? Then you guys go like, but Tech, you never talked about how this is what this is going to return. It's okay. We'll figure that out, okay? We'll let the compiler figure that out. Okay. So, but my concern is just to say, okay, can I call the function again and then add 2 to the return value so that that in return becomes my return value. Okay. So we know register A still has n in it. So that means, decrement A is going to give me n minus 1 in register A. We push it on the stack, and then we push the return address, LDI A dot 6 plus, decrement D, STDA, and then we do a branch, unconditional branch to the function that we are calling, which is function F, which is also where we are in. But that's okay. Okay, this is supposed to work, okay? Because as long as the caller and the callee agree, to the agreement, or they implement as agreed upon, everything should still work. So by this time, by line 33, the stack should be balanced. I should have the return value of f of n minus the f of n minus 1 stored in register A. I just need to add 2 to it. Increment A, increment A. There we go. All right. And get rid of the, you know, LDI A15 because that's not what we are doing anymore. All right. So save this code, run it first, okay, without even knowing what it is supposed to return. But that's okay. We'll figure out what it is supposed to return next. Now remember, this end is supposed to be a 3 this time. Okay, so we're gonna give it a test. Hopefully it doesn't work. Then I can show you what how to debug it, right? So now it returns a value of 0.5. So the question is that the right value to return? So the way to resolve this is to do it by hand. Okay, you don't even need to run the C code because what we do is we say f of 3 is f of 2 plus 2, right? F of 2 is f of 1 plus 2. F of 1 is just 1. Okay, so we back substitute. Whenever we see the f of 1, we go like, oh, that's just 1. 1 plus 2 is a 3. And then whenever we see f of 2, we back substitute and go like, oh, okay, f of 2 is just 3. 3 plus 2 is a 5. So having 5 being stored to location FE is correct. Are we doing okay so far with this approach? Okay. So if you don't trust your own method of verifying everything by hand, use the C compiler to help you. So let me illustrate what I mean by that. So now we go back here. I'm not checking in the program just yet, okay, because I want to double check with the C code. So I now copy the C code into this folder, mess up the C code, okay, so it reflects, exactly what we put in as, here. So we're going to comment out, the original right-hand side, and we put in the change code over here for testing purposes. Save the code, gcc-g-o fib.c, compiles just fine, gdb fib, put a breakpoint on line 13, sorry, line 13, run the code, print x, it is also 5. In other words, I'm double checking, okay? I did it once by hand, and then do it one more time using the compiler, just to make sure that, okay, it looks like the recursive call was done correctly. Are we good so far? All right. So now that we can do one side of the recursive call correctly, now we try to tackle the double recursive call. This is where the challenge is. All right. So now we go back here and we say, this is working. Cool. So now we want to get the actual code to work. So you go like, okay, we reverse these two because that's not what we want to do. So now we go like, okay, we have to implement the second call to function f. So you go like, okay, what are we supposed to do? Register A currently contains the return value of f of n minus 1. So I better not be messing around with register A. So you would think, right? So you go like, I'm going to use register B and register C to set up the second call to F. So you go like, okay, maybe we'll just do a LDI. First of all, okay, some people may say, oh, since register A has n minus 1, we'll make a copy of that. Then you have a contradiction already. Okay, let me say that one more time. Some people might think that register A still has n in it, but it also has the return value of f of n minus 1. It cannot be both, right? So which one is it? The return value of f of n minus 2. So some people might think then it's like, maybe I shouldn't be using register A to calculate, everything, and then we'll before we push it on the stack, we are going to save it somewhere. Okay, we're going to use a CPR BA. So register B now contains n minus 1, and then later on, since register B has n minus 1, I can now do a decrement B so that it becomes n minus 2, right? And then we can push it. Does that make sense? The reasoning the reasoning seems intuitive, but it's forgetting one thing. Okay, it seems logical, but it is forgetting one really important thing in the caller-callee agreement. So let's say I'm the caller and you're the callee. Okay, and I'm secretly saying, okay, register B is important to me, and then I call you. Okay, what is the agreement? Exactly. You can also overwrite register B according to the agreement. So when you return to me, everything is good, okay? You calculated the result. My assumption of register B still containing the value before the call, that is the wrong assumption. I cannot make that assumption. Is that okay? So that's why this approach does not work. So if this approach does not work, okay, let me reverse back to how the code is supposed to be, okay? What should I do? Well, okay, the first thing is easy. The first problem that I cannot preserve n minus 1 in a particular register, that's easy. I can just recalculate the whole thing, right? This time I'm going to use register B, do the whole thing again. Aha, okay, I got n back. Decrement B twice. Now we have n minus 2. Okay, cool, right? So, well, I better double check and make sure that is the case. Okay, so that means I can put a halt instruction here. Okay, but this time I also have to be careful because remember f is recursive. So that means if I go through a few recursive calls, the moment they get back to the first time with a halt instruction, it's going to stop over there. So that means I have to be careful with um, this kind of recursion and basically say, mm, I want something that only has one level of recursion. Okay, so the question is f of what would barely have one single level of recursion, which means it is going to have this thing minus one plus blah blah blah, and then f of question this one is not recursive anymore. So I need this to be a 0 or 1, okay? And in this case, because I'm still this is the this is the first call, this is before the second call. So that means this has to be the 1. So that means f of 2 is the way to test it. Are we good so far? Okay. So I need to retest it. Okay. So I make a comment here and say B should be 0 for testing. And then over in the main program, I'm going to have to remodify this line so that I say, okay, we are going to test it with 2, test with f of 2. And that's how the current code is supposed to set up. Are we good so far? Okay. All right. So let's go ahead and test this. Okay, save the code, rerun it. So by the time we get to the halt instruction, register B should be 0. And we should see it decrementing to 0. So it should start with 2, then 1, then 0. All right. So now we go back here. Yep, it's all good. And my own comment says B should be a 0 for testing, and it is 0 for testing purposes. So we're good. Okay, we know that we can recalculate the value of n after the function call, and that is no big deal. But now we have a problem. The problem is I need to set up a second call. Okay, so we'll go ahead and set up a second call, and then we have a big problem. So we'll go back here and say, okay, now that we know that register B has the um, has n minus 2, we'll just set up the call, the set of the rest of the call, which is push the return address on the stack. Um, and we're going to be careful, use the other register. We'll use register B, decrement D, stdb, jmpi to the function. This is the second recursive call, increment d. So right away, without even testing the code, I know we have a problem because at this point of time, by the time we get to line 42, what is in register A? What is the most recent call to f? F of n minus 2, right? What happened to the result of f of n minus 1? It got overwritten, okay? So now we have a problem. I need both. Yes. Oh, we got forgot to store. Oh, we forgot to push. Ah, very good. Okay, so we decrement, but then we forgot to store that, push it. Thank you. Okay, so that's pushing it. Right. So the question is, what am I going to do here? Okay, so let me state the problem. Okay, at this point, register A has f of n minus 1, and then at this point, register A has f of n minus 2. I cannot keep both at the same time. So how should I fix this problem? Hmm? You overrode n with, oh, okay, so you overrode n with the value of f of n minus 1. That will work, but that's not in the original C code. In the original C code, you're not supposed to change n. That is always another place to put it. You push it on the stack. Okay, so let me see if the instruction of the lab includes that, because in one of the classes I did, in this class I may not have done that. Okay, so let's do a preview. This one does not have it. Okay, so I'm going to manually go back to an earlier program because you have seen this technique already. You just did not think much of it at the time. Okay, so we're going to go back to params and return value, and then just go to the first question. So we go to, why is it howling? Mm, okay, so you guys can focus on this code here while I investigate why it is howling. Hmm, I guess that's why most people open the door. It's not too noisy right now. We can do it. Yeah. All right. So let's check out this program. Okay, this is pretty easy. Okay, 5 just returns a 5. Okay, that's not a big deal. So when we get down here, this is initializing the stack pointer. This is pushing the return address. We get to 5. And then what are these two instructions doing here? What does it map to in terms of stack operations? It pushes A on the stack. It pushes the return value of the first call of 5 on the stack. So that means that thing is on the stack now. Nobody can touch it. And then what do? We place a second call. Okay, so from here all the way to here, that's my second call to F, which means by the time we get here, we have um, register A containing the return value of the second call of F, but the stack pointer points to the return value of the first call to 5. So by loading whatever the stack pointer points to into register B is now the return value of the first call to 5, when register A is the return value of the second call of F. So by adding those two, it ends up with a value of 10. So that's the trick, okay? The trick is to push it on the stack and then pop it later. But it is not a local variable. hmm Did it work? All right, well, we're gonna have to test it. Okay, anyway, so at this point we can go like, okay, we can do that. So that means we push it on the stack at this point. So we say decrement D and then stda. And then for people who notice that, oh, we just incremented D and then we decrement again, so can we just kind of delete both of these instructions? The answer is yes. Technically, you can, because functionally it would be doing the same thing, but conceptually, I would not recommend it. Conceptually, the increment D is for deallocating the argument that is still sitting on the stack, which you should do anyway for every function call, is to deallocate all the arguments. The second, or the, I shouldn't say the second, but the decrement after the increment is for reallocating the same byte to store the return value of the first call, which is f of n minus 1. So this means now I'm pushing f of n minus 1 on the stack. Okay, so by the time we get back from the second call right here, that means we can now pop the um, f of n minus 1 from the stack into register B, which is LD BD, and then increment D. So now A should be f of n minus 1 when register A still has f of n minus 2. When I add those two together, that should work, right? Except it also does not work. Except this also does not work. So you go like, how is this not going to work? Well, let's run the code and see how it is broken, and then we'll try to figure out why this is not working. Are we good so far? Okay. So we are intentionally running the code that is known not to be working, but we need to find out why it is not working because I have not told you so yet. So we'll run the code, and this time it's going to take longer because I think it's going to go for endless recursion, or at least a lot more than what we expected to do. Now remember, we are still testing with f of 2, which is the marginal case for a recursive call. All right, so now we go back to the trace over here, and we go like, whoa, look at this. I don't think that's supposed to happen. Okay, so when something is not supposed to happen, what do? You track it until you find out where it deviates from what you expect. Okay, and the best way to track that is to look at what we do on the stack and what the stack pointer has. Okay, this is predictable. This is predictable. This is pushing the 2. This is pushing the return address from F back to main. Okay, and this is the recursive call. Okay, we're pushing 1 on the stack, and then we're pushing the return address from F back to F. And then we go like, wait, hold on a second here. What are we doing that? Okay, so this is still correct. Okay, this is after. Okay, let me show you just graphically what we are doing here. We are trying to calculate f of 2. Okay, so we're trying to calculate f of 2, which is f of 1 plus f of 0. F of 1 is good, okay? Because by the time f of 1 is returning, it is returning a value of 1, which I can show you exactly where the return value is specified, that one over here. So this one is returned back to the caller, okay? And then it's supposed to call f of 0. So that means it should push a 0 as the argument after we save 1 on the stack. So the where we save the 1 on the stack is right here, and then it should push a 0 on the stack, but instead it pushed 4, 4 on the stack. This is the first observable point of deviation. Are we doing okay so far? So once you know the earliest point of deviation, which is not necessarily the actual point of deviation, then you go back. You track it backwards and figure out, why did I push a 44, 4 on the stack? So you go like, okay, this is the doing of line 4, 4, and this is okay because it is supposed to kind of decrement the stack pointer. This means register B was a 4, 5. This means register B was a 4, 6. And this is asking, where did I get the 4, 6? And where we got the 4, 6 is from location FC. You go like, location FC? What is that on the stack? So now we go back to the stack and then we ask, what is happening in this particular program? Okay, so this is unknown at this point. This is a 0, 2. So the way the stack worked out is like this. So in order to calculate f of 0, 2, we push 0, 1 and the return address. Then it returned. When it returned, these two would be gone. Okay, these two would be gone after it returned. Then we push the return value of f of 1 on the stack. So this location becomes the 0, 1, which we observed. Then we call f of 0 after that. So that means this should be f of 0, 0, which is f of n minus 2. This is supposed to be n minus 2. But instead of n minus 2, it became 4, 4. And 4, 4 is double decremented from location FC. So what is at location FC? Location FC is the return address. So now the question is, why are we off by 1? We're supposed to retrieve this one here. Why are we off by 1? So you move backward again, okay? Because we know that we got the wrong address, right? Okay, so we move back. Okay, so we know this address is off by 1. Then you ask, why did we get it off by 1? We are getting a 0, okay? The 0, 1 is still the correct offset, okay? So when I said the correct offset, I also have to qualify, because is it the correct offset from the base of the frame, or was it the correct offset from where the stack pointer points to? Those are two different questions. Let me say that one more time. Is it the correct offset from where the base of the frame is? Yes. Is it the correct offset from where the stack pointer points to? The answer is no. Because where is the stack pointer pointing to at this point? If I go back to the display here, after we push the return value of f of n minus 1, this is where the stack pointer points to. But what is the actual base of the frame? The base of the frame is actually here. So by pushing one additional item, we just changed the stack pointer, so it points to 1 byte below the actual base of the frame. Everything is now off by 1. So that means the fix is to add 1 to the offset. Okay, there are a few ways to do it. You can do it. This is the easiest way to do it. Is to simply add 1 to the offset, because the stack pointer is pointing to 1 byte below the frame itself, because we push some additional item. Are we doing okay so far? Okay, so now what we do is we go back to the trace, and then we go to the same location where the problem is. In other words, the first thing that we can observe, or the first thing that we can easily observe, is this one here. We're supposed to push a 0, 0. So we put the cursor of the spreadsheet over here. So this way, we keep focusing on exactly the same spot, because the change to the program should not move anything. It will change the value, but it's not going to offset, anything in the trace. So now we go back here, make sure we save the code, and then we run it again. All right, so we switch back. Aha, this time it works. Okay, and we also want to double check, at the end of the program, did it end? Yes, it did end. We ended up, in the halt instruction. That was intentional. It's not supposed to be a 0, 0 here, but everything it's not going for the infinite recursion anymore. Okay, so now we can go back to the source code and take out this halt instruction, okay, which has the wrong comment on it anyway. The rest of the program should work. And we are still calculating f of 2, which should be a 1. So with this test code, we should be seeing a 1 being stored to location fe, which is x of main. So we now go back, watch the whole thing terminate. It stores a 0, 1 to location fe. So that's good. Okay, but this is a test code. It is not f of 3. So now we should test it with f of 3. So we go back to our editor, go back to main, change the 2 back to the original 3, like so, and then run the code again. But before we look at the actual trace, now we have to work this out by hand. I just erased it, but we got it already, worked out already. So now we ask, what is f of 3? It is f of 2 plus f of 1. F of 2 is f of 1 plus f of 0. F of 1 is just 1. F of 0 is just 0. 0 plus 1 is a 1. So 1 goes back here. This is f of 1, which is going to go to here again, which is just 1. So we have 1 plus 1, which is a 2. So f of 3 is supposed to be 2. So now we go back to the analysis tab, and it goes a little bit further this time, which is fine. But we are seeing that the 2 is stored location fe, which is x of main. We get to the halt instruction, the stack pointer is balanced, so all is good. So that trick, so there are two tricks in this case. One is pushing the return value on the stack first and then retrieve it later. The second trick is once you push something, you just moved the stack pointer. The stack pointer is no longer pointing at the base of the frame. So if you need to reference anything on the frame, you have to account for the extra things that you just push on the stack. So those are the two takeaway from this particular implementation. Yep. Hmm. It's okay. Okay, but it is the approach that is important. Okay, it's the approach which is testing it step by step. I did not add too many lines of code each time. I test it first. I know I I figure out what should be on the stack, what I should be seeing. I verify it. If it doesn't work, I go back and check it again. All right. So what about the new program, the one that is due on Wednesday? Are we still working on it okay? Okay. You haven't started? Huh? Oh, okay. Well, since we do have some time left, okay, which is about 15 minutes, I would go, we'll take a quick look at that one. So we're going to go back to the commit line, go back to use the editor to point there. Okay, before I forget, I'm going to send this to you, all of you. So let me go to announcement and send you the solution of fib. See attached. I will just send you the TTP ASM file. Hmm. For the final or for the homework? For the homework. Yeah, the final is pretty hard to. I mean, for the final, you don't have access to the computer, so I cannot you know give you a flat zero if it doesn't compile. Yeah, but for the homework, I think it's reasonable. Okay, because I think for the homework, people who do not even put the code into the assembler just to check it out or at least to test run it to a certain point, I don't know how that can happen. Yep. Mhm. Mhm. Mm. Yeah. The only, as far as I can tell, it doesn't usually do that, but it can potentially if it's too big. So what you can do is to go to File. Where's my cursor? There we go. So you can go to File, go to Version History, and just revert it back to an earlier version, like previous day. That would be usually the best way to do it. So you can go to see his version history. Now mine is ancient because I've been using it for years. So yours is not going to be nearly as ancient. You can just point it to the previous day and say restore this version, and it should be fine. Yep. So that's how you kind of restore back to an earlier version. Yep. Uh, Before I forget, okay, it is sent. Okay, so this way you guys have my solution, which is also a way for you to practice, which is to comment the code. Okay. Um, all right. Yes. Back to the new assignment, the assignment that is due on Wednesday. Okay. So that one is called struct2. So we're gonna unzip struct2. I have the zip file already downloaded, or I think, or maybe not. Nope, I forgot. Okay. All right, let me download it first. Where is it? Nope. Okay. Let me just get to it first. Okay, that's the one that is due on Wednesday. And in it, I think this one does not have it. This is just the submission. Okay, got the wrong one. This one. So there we go. Preview would be fine. Just get to the last page. This is the file that I need to download. Okay. All right. So it has two programs here, struct2.c. So we'll start with the C code. All right. So obviously, the line that is messy is this one here. This is the only recursive call, but this one is not a double recursive call. Okay, it is a single recursive call. So that means the rest, it looks complicated. Okay, but it is not terribly complicated. So the first thing you might want to do is simply to ignore the recursive part and really just specify um, you know just specify constant here. Okay, so the whole thing does not do much except to um, okay. Let me let me show you instead of talking about it. Let me show you what I mean by that. Something like that. Okay, just to make sure that you know how to do the compound assignment. So do that first. Okay. Now, how do you know you got the implementation correct or not? You can tell because whatever this pointer points to, you can run this code in C++ or C, and then observe the value of y when this is all done. Your assembly code should do the same, okay? And it should also do the same with x. So just make sure that your code is consistent with this C code. Then that means you have the compound assignment already done correctly. So that would be the first thing that I do, is to make sure that the compound assignment operation is done correctly. So assuming that part is done, then obviously this is the only other part that is kind of mysterious. So now the question is, how do you do this? It starts with answering the question of what am I passing as my parameters? So we'll start with the first argument. We'll start with this one. This is the first argument. So the first argument is the value of member n of the structure that is pointed to by PTR. Okay, so that order matters. Okay, and the fact that it is the value and not the address of also matters. Okay, so that's number one. Then we move on to the second argument. So now we ask, what is the second argument? What is it really passing on the stack? The second argument is the address of member V of the structure that PTR is pointing to. Okay, so that's important. Okay, because once you know what you're looking for, then you can check whether you call the function recursively correctly or not. Are we doing okay so far with that? Yes. Okay. There are a few things you can do to kind of simplify this so that you can check whether it's working correctly or not. You can always simplify the C code and then make sure that your assembly code matches the C code, and then add more things back to the C code. Check the C code with GDB, and then make sure the assembly code works again. So you can basically mirror all the changes and add complexity back. Second tip, N1 is the most complicated case in the recursive call. So if you want it to be um, the easiest recursive call, okay, so let me show you what I would use to test it. I would do a 0 here. Just give it a null pointer. So think about what a null pointer is going to do. If you pass a null pointer, that means PTR is going to be null. If PTR is null, this check is going to default to the else case, which is just returning a 0. So that means whatever VPTR is pointing to should remain the same. So y would remain the same, x should also remain the same, but since x was never initialized, so x would just get the value of y. Is that okay? All right. So that's what I would check first. Now, if that works out, okay, then you modify the code and start with n1 bracket 1, 2, 3, 0, 1, 2, 3. It'll be the second to the last one. Actually, I take it back. It should be the last one. So change the C code to this. So in this case, it should just be the 9. In other words, because it would go for one single recursive call, but by the time you get to the recursive call, PTR points to n would be referring to the null pointer here. So it would do one single level of recursive call. The recursive call is going to end up with the first argument being 0, which we have tested already. And that's why I want you to test first with the N1 part here being 0. Because if that part works, that means you can end the recursion correctly. All right. And then you test it with the other one, okay, which is N1 bracket 4, because that one only involves one level of recursion. So if it doesn't work, okay, then it is the recursive part that is not working. Then you can focus on just debugging that part. Is that okay? So if that works, then you move up, okay, you go to the second to the last element. So this time it will have 2 levels of recursion. And if that works, I think generally speaking, the whole thing should be working. So are we doing okay so far in terms of understanding how to do it step by step so that you don't end up with a large program that is not working and you don't know where to start? Okay. Are we doing okay with this? All right. All right. Well, the time is 45, and I think I'm good with all the content that I need to talk about. Do you guys have any questions? Not until Wednesday. Okay. So on Wednesday, I will give you guys the solution to this particular homework assignment. Um, Once again, the key is to work on it step by step. Okay, watch what the C code is doing. Okay, because the key is to look at the C code and try to use the C code to give you a clue of what it is doing. Okay, and well, since we have 5 more minutes, I will show you how to use GDB to help you in the process. So we'll go ahead and gcc-g-o struct2 struct2.c. We'll I'll go through GDB once, to kind of give you guys some idea. Okay, we'll put a breakpoint on line 23, run the code. Okay, single step. Okay, so this is the first recursive call, and okay, so and it will call recursively, and then call recursively, and then call recursively, and then call recursively, and then one more time. And this is the terminating condition. The reason why I know this is the terminating condition is PTR is now a null. So that means it would do how many levels of calls the way it is set up? It would do 1, 2, 3, 4, 5, 6. So there are 6 levels of recursive call, and this is why it is messy to debug using the code as it is. So that's why I recommend do not do this. Instead, test the code. Okay, let me comment this out. So instead, test the code with just 0. Okay, because that would not have any recursive call. It should just return a 0. Now, if you have a 1 over here, it would do 1 level recursive call. Okay, not one. It's n1 bracket 4. So this one would go for 1 level recursive call. Okay, and we compile. Oh, okay, I did something. Oh, I forgot the address off. Okay, that's my bad. Okay, I forgot about that earlier. So if you want to use any specific element, you have to specify the address of, because it has to be passed to a pointer. So it has to be the address of a struct node. So with this one, it should go for 1 level recursive call. GCC GDB. Oops. Put a breakpoint on line 24. Run it single step. Okay, and you can see that this is n1 plus 64, which is the fourth element of main of n1. Now n1 is a global variable, so if you want to know whether that really is the case, you can actually use the address of n1 bracket 4, and you can see that they are the same. They both end with 8060 8060. So this means you can tell for each recursive call what PTR is supposed to be. It is supposed to be the address of which element of the array. That part should still be the same in your assembly code. So if you observe what is pushed on the stack, you should be able to see that. Now, because it's also a single point recursion, so you don't have to worry about we grow the track, we retract, and we grow again, and then retract again. This is single direction. It keeps growing, stops, and then backtracks. So that makes it easier for you to debug because you can see how the stack pointer is just decrementing, and then you check the content, what you're pushing on the stack until it stops. Okay. If everything looks good, that means the forward motion, which means the actual recursive call is being done correctly. Now, if it goes back and then things starts to break, that means it is after the recursive call that something is not working. Okay, so that helps you to identify at which point the program is not working. So I hope that helps a little bit. Okay, all right. So try your best. Okay, I know this program can look difficult. Okay, but if you try to kind of, the more you try to work this out, the more you're actually learning. Um, and I'm always still having office hours, from 8 to 9 every morning. That includes tomorrow and the day after. Okay, so that means you can still kind of come visit me if you're really close and you go like, okay, but I'm just not getting this part to work, but every part seems to be working. I can still take a look at your program. All right. So I will stop the lecture, and there's no lab today because I'm out of labs now. I'm not sure that's a good thing. I'm not sure that is a good thing. I do have another recursive, struct program that I can assign, but since Thanksgiving is happening this week, I'll give it to you after Thanksgiving. So you can do this one when you're eating, leftover turkey and pumpkin pie. Hmm? All right. Did I give you guys, the final exam or a sample of that? Okay. So start looking into it. Okay. Don't get obsessive. Okay. But start to look into it. Look at the C code first. That C code does compile. Okay. So I would suggest you to at least compile the C code. Use GDB to kind of give you an idea of what the C code is doing before you even try to look at the actual assembly code and try to fix it. All right, so I'm going to stay here if you guys have any questions, or for those of you who want to continue to work on your assignment that is due on Wednesday and you want to work on it here and want me to take a look, I will still be here. But if you think, okay, I'm good, then you can also go get your early lunch compared to the usual Monday, Wednesday. That's up to you. All right. So I did record the whole thing. I did not make a poo-poo. Sometimes I forget to click start recording.